Hi everyone, I'm Yujie. I'm a third-year PhD student in population health, data science, and digital health CDT. I'm also working for the Ask JGI in the Jane Golding Institute. Today I'm gonna delivering this training and hope it will be helpful for you to know more about the tree-based structure machine learning algorithms. So I guess I would just share my screen and then you can see it. Yes, so I will go through this tutorial, but if you get any questions during the training, please feel free just to send the messages in the chat, and he will help me to answer part of them. But I will also go through all the questions at the end. I will quickly go through the outline of today's training. So basically, it will be about 6 parts. I'm gonna go through, introduce what is exactly decision tree and how does it work. We will also use an example to see how can we construct a decision tree in Python. We will do some preparations for the data. Well, we will use the data from it's called wine data set from the scikit-learn. So you don't have to download it. You can just easily import it from the scikit-learn passage. So it will be super straightforward. So based on the data, we will train a decision tree model on it. Then we will do some evaluations to see how the performances is. And then I will talk a little bit about the overfitting issues. You probably have heard it before. At the end, I will introduce another algorithm, which is called random forest. I will talk a little bit about how this algorithm solve the overfitting issue from the decision tree. Well, why decision tree is important? Because you probably have heard of a random forest or gradient boosting algorithm. They are more often used, but you will need to know the basics of the decision tree about how it works to understand those more complicated algorithms better. So I guess I will just go to our main parts. So what is exactly decision tree? Well, actually, decision tree is a very popular and also very easy to understand algorithm. You can use it for classification and regression problems. So you can think of it as like a flow chart to help the computer to make decisions by asking a bunch of yes or no questions about the data. So here is a very simple example about how we can classify the vehicles. So the first question, like based on this decision tree, the first question, the model is asking, okay, does it have an engine? Or if it's true, well, how many wheels does it have? Does it have the number of wheels more than 2? If it's true, it will be classified as car, well, otherwise it will be motorcycle. But also if you if it doesn't have an engine, we will just classify it as a bike. So this is a very, very simple example. So the root each root, which are the rectangle points here, represents an input variable and also a condition of that variable. And each of the leaf nodes here, which is a circle shape here, represents an output variable, which is used to make a prediction. So the example I'm showing here only have 2 branches, or you could say binary split. But you can also construct a multi-branches tree, like more than 2 branches. But this training will only focus on binary tree, which is also default in scikit-learn as well, and also is also like very popular usage in the machine learning area. Here is another very simple example to to have a binary classification with two features in our data. And the right plot here shows the scatter plot of the data points we have and how the decision tree does the split. So we can see the first split is built on the feature X2, and they decide the split based on the 6t, the value of 6t. So the decision tree, the model first split the data into two groups. It's above 6t and below 6t based on the X2 feature. And if we go to the right branches here, we will go to the second split, which will be here. So if it's x1 variable, it's less than 50, so which will be this area, it will be classified as green class. Otherwise, it will be classified as a red class, which are the similar steps we'll go through from the left branches here. So you can split the data into different areas, and then you can classify it. So, so this is a like very, I'm just trying to give a very rough picture about how the decision tree looks like. So now we're gonna go through the deeper steps. So how does a machine learning construct a decision tree based on your data? So the steps the algorithm is taking is that the computer will look at all the data you have, and they're trying to find the question that best split the data into different groups. So it keeps repeating the steps where they will find the best split point of each variable, and then they split the data into different groups, and then within each groups, they will repeat similar thing. They will find another split and get more branches, and then just like repeat. So it will stop when all the data in a branch belongs to the same category, or when the tree reaches to its maximum depth. So the maximum depth is our argument that or a hyperparameter that you can set in your coding part, where you can set like what's a maximum depth number I want it to be. We will get to there later. So this is the general idea about how the machine learning constructed the decision tree. But also, we want to know more about like how does the decision tree decide the best way to split the data. So what the algorithm does is that at each of the nodes, the algorithm will look at the split point that they're trying to split the data into the most pure subsets. So ideally, what we're trying to get is that after the split, all data points in one branch will all belong to the same class. So like the most pure subset. But in real world, the data is more like more messy. So we probably won't like get into cases where all data points belong to one class, but we're just trying to increase the purity as much as possible. But how does a decision tree measure the purity or impurity? So what we have here is I'm gonna introduce two impurity measurements that are widely used in scikit-learn package. So one is called Gini impurity, and the other is called entropy. Here I showed a plot about how the shape of the two measurements looks like. I won't go too much details about the mathematic part, but what I would like everyone to know is about how the Gini and the entropy how it ranges, and also how can we interpret it. So for Gini impurity, whenever so it ranges from 0 to 1. When Gini equals to 0, it means like you get a perfect pure nodes. So all the data points belongs to the same class. For binary classification problem, the maximum Gini will be 0.5. This kind of indicates that this is not really impure. This is not really pure, sorry. And also in this case, data points are evenly distributed among both classes. For multi-class classification, where you have more than 2 classes, Gini can be higher than 0.5, but it's always less than 1. For entropy, it's similar. So when entropy equals 0, which means all instances belong to the same class, in binary classification problem, the maximum entropy will be 1 when all the classes are evenly split, like 50% versus 50%. For multi-class classification, the entropy will increase, but it depends on how many classes we will have. We also have another, okay, I'm gonna introduce like for Gini and entropy, in which cases you would use them. Well, when you're constructing the algorithm, I would suggest maybe you can try each of these measurements. You can see which performs better. But in general, Gini is faster, but it takes longer for entropy calculation because it involves a log calculation. You can see from the mathematical equation here. So it takes longer to get the calculations. But sometimes with the imbalanced classes in your data, entropy may perform better. So you can try it out and see which one performs better. Here's how it looks like among the 2 measurements. So you can see like for the Gini, which is a red line here, the maximum it can get is a 0.5 in binary classification, whereas the entropy equals 1 is a maximum. And this maximum values means that your data is not really pure. The scikit-learn package also provides another measurement, which is called log loss. But I wouldn't talk about more here. So if you're interested, you can just click this link and to know more about it. So this is the general ideas about how the decision tree works, and how does it measure the purity of the split and to construct the decision tree. Here now we can go to the coding part and see how we can construct a decision tree with the Python code. So first, we're gonna explore a little bit about the data set that we're gonna use. Today, we're gonna use the wine data set from the scikit-learn. We can import it easily using the code here. And then we can print out the structure of our data set and also to find out how many classes we have in this data set. So what we can see here, we have about 178 samples in our data set, and there are 13 features. For the labels, we have 3 classes. So we're gonna do a 3-class classification problem here in our example. We can transfer our data into a data frame, and then you can use this display function to see how the data looks like. And what you can see is all the features we have are numerical features. And if you're interested to know the potential correlations or patterns between each features, you can run the code. You can use the pair plot function from the Seaborn package. And then if you run the code here, it will give you this type of visualizations where the diagonal of the pair plot displays the distribution of each feature. among each of the classes, and others, the scatter points here is a correlations between two features. Apart from that, we can also see like the distributions of the class distributions of our data. So how many data points are there in each of the class? So in our example, we have 71 samples belongs to class 1, and 59 belongs to class 0, and the rest of them belongs to class 2. We can also use the code here to print out to see if there are any missing data in our data set. So if you run this code, you will see, well, obviously this data set is very clean, so we don't get any missing values in our data set. So after you get an idea about how the data looks like, we can get into our model training section. So first, we're gonna split the data into the training and testing set. You can use the train test split function from the scikit-learn package. I'm gonna talk a little bit about the random state here. So you probably have seen this theme before. So this random state can be used to ensure that you can reproduce your experiment. So meaning that if you set a specific number for the random state, and when the next time, if you use the same number, you will get exactly the same results every time we run the code. So this might be very useful if you want to reproduce your experiment, or if you want others to reproduce your experiments, you can set the random state at the same with the same number to make sure you can get the same thing every time. Because if you don't set the random state, the data will be split randomly, and the data you get will be like very different every time. Yes, so if we run the code, we will split. So here, what I did is I put 80% of the data as the training set and the rest of them as the testing set. And this is how it looks like. And then we can train the decision tree model, use the decision tree classifier from the scikit-learn package. I first set the max depth of 3, and I choose the Gini impurity measurement. And if you fit the model, and then you can visualize the tree and to see how it looks like. So it generally looks like this, but also you can play around to see, okay, if you set them, you can play around the max depth of different numbers. You can first, well, if you want to try from 1, which actually is a little bit meaningless, because if you only have like 1 depth of the tree, which means you can only split the data into 2 parts. But obviously we have 3 classes of our data set, so max depth of 1 doesn't really make sense. So I guess it's better for us to start from max depth of 2. And if we retrain the model, we can visualize the tree. And this is how the tree gonna look like when setting the max depth of 2. I'm gonna talk a little bit about the decision tree shown here so that you can get an idea what it's telling you, because there's so many stuff here. So for the root code here, so for the root node here, what it's telling you is that the algorithm uses the color intensity as the first feature to split the data. So it split the data into 2 parts with the value of 3.82. It's telling you that the Gini score at this stage is 0.659. And at this stage, we have 142 data points. And the value here is telling you like the distributions of the classes, like how many data points are there in each classes. So obviously it's telling us there are 45 data points in class 0 and 57 data points in class 1, and the rest of them belongs to class 2. And the last one here, the class is telling you which class get the majority data points in this stage. So we have 57 data points, which is a maximum number, belongs to class 1. So that's why we get here class equals to class 1 here. So after this split, if we go to the left branches, it uses the proline as a second split to split our data. I think proline is an acid in a protein, yeah, or something like that, but I'm not an expert of it. But basically, I think the model decided to split the data using the proline with this value. And this at this stage, you can see the Gini score, it's a little bit, it's a bit smaller comparing to the first split. And also after this, the first split, we got the samples of 52. And among the 52 data points, we got 3 data points belongs to class 0, and the majority of them belongs to class 1, and that's why we got the class equals class 1 here. Yes, and after after this, we can split the data into 2 parts, and then if we go to the left one here, you will see the Gini score is a little bit smaller than the previous one. And also what you can find in this orange square here is that the Gini score becomes to 0, which is what I said before about that when Gini equals to 0, which means your branch is really pure. So here we got 2 samples and all of them belongs to class 0. That's why we got the Gini score as 0 here. So after we got the decision tree, we can evaluate how the model performs on the testing set. So we're gonna predict on the testing set, and then we can print out the classification report. We can also make a confusion matrix. It looks like this. I found the confusion matrix very helpful and also very easy to understand whenever you're trying to evaluate your model. So basically, what it tells you is it will show you a table layout like here to show you the performance of an algorithm. You can easily see how many cases are predicted correctly and how many cases are not predicted correctly. So here, all the diagonal cases here means like those data points are correctly predicted, but we can see there are 5 data points are not predicted correctly. So for example, there are 3 cases where the actual class is class 1, but they are predicted in class 0. Yeah, so I think this is very intuitive to see how it performs. What we can do also here, if you want to, we can go back and see if it's max depth of 3. And the tree will look definitely a little bit like deeper than the previous one. And before when the maximum depth is 2, we got the accuracy of 0.86. But if we increase the max depth to 3, we get the accuracy of 0.94, which increases a little bit. And if we plot the confusion matrix, we can see there are only 2 cases are mistakenly predicted. Well, we can also like visualize how the accuracy score changes over the different max depth argument. For people who don't know what accuracy is, I put a very simple equation here. So basically, accuracy means how many cases are predicted correctly among the total predictions you're gonna make. We can use the code here to visualize how the accuracy gonna change with different max depth arguments. I used a for loop and saved all the accuracy into a list, and then I'm gonna plot the list, the accuracy we have got here, and you can see this is how it looks like. So the blue line represents the training accuracy, so accuracy in the training set, and the orange one is in the testing set. But what you can see here is that the model performs generally very well. You can see in the training set, it can reaches to like accuracy of 1. And also for the testing set, you can see the accuracy doesn't change after the max depth over 3. But this is actually very suspicious because the wine data we used from the scikit-learn is very simple and clean. But this is not common in real life because usually the real life data set are more noisy and also more complex. So what we can do here, yes, so before we try different way, so I'm gonna talk a little bit about the overfitting issue. You probably have heard of it before, but basically, so when we get more complex data set, decision tree kind of brings the overfitting issues. So what is actually overfitting? So overfitting can happen when a machine learning models learns too much detail from the training data, including its noise and also those random fluctuations. So instead of capturing the general patterns of the data, the models memorize the data, which is a little bit stupid. And also this kind of hurt its ability to make predictions on the new and unseen data. So if we imagine, if we use an example to explain this, so imagine a student who is taking an exam, but what they did is they memorized all the answers from the past exams instead of understanding the core concepts. So they also like, they also remember all the mistakes or irrelevant details. This is definitely not helpful when they're taking a new exam. So the student may perform like very bad in the actual test because they focus too much on memorizations rather than understanding the general picture of the concept. So that may happen in decision trees as well, because in decision tree, overfitting can happen when the tree becomes too deep and too complex. It can like perform perfectly on the training set, but performs really bad on the testing set. So what you will see is that if there is overfitting issues, you will get a very high score of training accuracy, but the accuracy in the testing set will drop a little bit. To understand this better, what we can do is that we can complicate our data set a little bit and to add some noises by ourselves and to see how it looks like. So here I added some noises in the data set and also added a little bit of irrelevant random features. I call it X noise. And then we can repeat what we have done before. So we split the data. We get the accuracies among different max depth. Then we plot how it looks like. So from this plot, what you can see here is the model performs really good on the training set. However, there is a drop of the testing accuracy when the max depth is above 3. So which means like there is an overfitting issue in this case. So if you are interested, you can plot the tree and how it looks like. And what you can see here is that it includes a irrelevant feature here where we call it random one, which is something I made it up and added into the data. But it included, the algorithm included this feature as a way to classify the data, which doesn't make sense. So in this case, we can kind of feel like, okay, there is an overfitting issue. So how we gonna solve the overfitting issues? There are different ways to improve that. For decision tree itself, you can also do some prunings. But today, what we're gonna do is we're gonna introduce another algorithm, which is called random forest. It's more robust than decision tree. And yeah, it solves the overfitting issue better. So what is random forest? Well, it is actually an ensemble method that include many decision trees. And then they combine the results together to make more stable predictions. So for random forest, it has multiple independent decision trees. So they train each of the tree independently with the following concept. So in random forest, each tree is actually trained on a random subset of the training data instead of the whole data. And also in random forest, for each tree in the random forest, they only pick a random subset of the features instead of including all the features from the data set. So this can add like further diversity of the trees. In random forest, we don't have like explicit depth control as in decision tree. So in random forest, it doesn't limit the depth of each tree actually. So the trees will grow naturally based on the data they are given. But if in this case, how does the random forest will make the decisions for the prediction? So in random forest, it uses something called the voting strategy. Since the tree is grown independently, so the final prediction will be made by aggregating all the results from all the trees. So you will see like, okay, if the majority of the trees think this prediction belongs to class 0, then we will go for, okay, we agree with this. Then we're gonna make the decision that the classification will be class 0. So in this type of, using this type of strategy, it kind of can reduces the overfitting issues because even though there are like 1 or 2 trees are overfitted, for example, if they grow too deep, the ensemble average will kind of like smooth out their influence on the final prediction. So this is why the random forests are more robust to the overfitting issue compared to a single decision tree. So that's how it works for the random forest. Here is a quick example about how we can construct a random forest classifier in Python. We're gonna use this function from the scikit-learn, and we're gonna do similar things and to print out the accuracy among the training and testing set. But also you can visualize how it performs comparing to the decision tree. Well, what you can see here is that the random forest overperforms than the decision tree. It reaches the accuracy of 1 for both training and testing set. But just to clarify, this is because we're using a very simple data set. The wine data set is very simple, but in real life, if you get something like 100% accuracy among your training or testing set, you may have to like double check if there is something wrong, because in real life, the data set might be more complex, obviously. But in here, I'm just trying to give a broader idea about like how the random forest can overperform comparing to the decision tree. You can also plot out the feature importance using the code here to see like which feature is the most important ones to make your to help the algorithm to make the decisions. So from the random forest we just built before, we can see the color intensity is the most important feature, and followed by proline and others. Well, if you want to know more information about the feature importance, you can click the link here to see how do they actually calculated the importance score here, but I wouldn't go to too much details about it now. Yeah, so this is the general structure about what is a decision tree and random forest. If you're interested, you can also do some like simple exercise by yourself. I would suggest you can try to build the decision tree classifier and random forest classifier on another data set, for example, the breast cancer data set, which is something you can import from the scikit-learn. And then you can try load the data and do some preparations for the data, and also fit the model on the training set, and also evaluate how it performs on the training and testing set. If you are interested, you can also read some like more information about the decision tree and random forest from the scikit-learn. I also put a link about the XGBoost here, because XGBoost is a very popular algorithm that are used in research as well. So if you want to know more about it, this is the paper about the algorithm is in this link. And there is a Python package of how you're gonna use Python to construct an XGBoost. Yes, I think that will be everything about the things I want to talk about today. I saw there are so many messages in the chat, but I haven't gotten time to look at it. So I guess there are many questions.
That was great. Thank you so much, Yujie. Could you, Pao and I were answering some of the questions that were happening as you were speaking, but would you be able to elaborate on how people are using decision trees in cases where there's missing data?
That's a very good point. So I think if they got the missing data, there are what I would suggest is you can deal with it when you are doing the pre-processing of the data set. And also it depends on what type of missing is that, because they are missing at random or missing at not random. So that's it's a very big question. But the easy thing people gonna do is first, the easiest way is that you just remove those of the missing data. But also what you can do is like you can do some imputations of the missing data, maybe based on, I don't know, median values or average values, whatever you think might be better. To impute this missing data, and then you can build the model upon that pre-processed data.
That's great. Thank you. Yeah. Yeah, that's useful. I suppose the people who might be taking this exercise away, the data they're looking at is hopefully data they know quite well. So if they see missing data, then it's on them as the context experts to go, oh, hang on, this entire column is missing. That means something's gone wrong with data collection, or oh, this is just random. So yeah,
Exactly. And also, I think there are like more complex aspect where people gonna build machine learning models to predict the missing values among your data set. So, but that would be a completely different picture, completely like a more specific research area to dig in.
great, thank you. Were there any other questions for Yujie?